Right now, as you sit in front of a screen on a quiet planet, something is happening above your head that does not feel quiet at all. Somewhere in the darkness, in a galaxy so far away that its light began traveling before complex life ever crawled out of Earth's oceans, a star is dying in the loudest way the universe allows. In the time it takes you to blink, it releases more energy than our sun will burn through in 10 billion years, and it pours that energy into a pair of razor-thin jets that slice across space at almost the speed of light. Most of that violence will miss us completely, but not all of it. A tiny fraction of those photons, the highest energy gamma rays nature can produce, are right now racing through the cosmos, invisible, unstoppable, threading their way between galaxies until, by sheer geometric coincidence, they wash across the small metal skins of NASA's satellites orbiting Earth. Those machines are listening constantly. They do not sleep. They count every incoming particle, compare it to decades of data, and decide in milliseconds whether what they are seeing is ordinary cosmic weather or something far stranger. Very recently, they saw something stranger. A single burst slammed into our detectors with a brightness no model had predicted, a spike so sharp it temporarily overwhelmed instruments designed to study the most extreme explosions in existence. Almost nobody outside the scientific community understands what that moment really meant, or what it quietly implied about how fragile planets like ours might be. We tell ourselves the night sky is peaceful, distant, decorative. By the time this story is over, that description will feel like a comforting lie. You will still look up at the same stars, but you will no longer hear the word safe in quite the same way again. To understand what those machines actually heard, and why the numbers on their screens made the veteran astrophysicists fall silent, we have to rewind the story and look at how we first discovered these explosions in the darkness between galaxies. My name is Mohammed Afnan, and this is The Hidden Cosmos, where we tell the real stories hidden behind space headlines, without the fake drama and made-up conspiracies. If you want cinematic journeys built on numbers, missions, and papers, you can actually look up, hit subscribe, and turn on notifications, because we go this deep into the universe every week. The burst you just heard about is not science fiction. It is a real event recorded by real instruments, and the word terrifying belongs to the physics, not to any clickbait title. To understand why this detection shook veteran astrophysicists, we have to rewind. Gamma-ray bursts were once thought to be distant, harmless fireworks at the edge of the observable universe. Before NASA learned better, it quietly launched a fleet of satellites with one job: to listen for those flashes in the dark. That is where the story truly begins. Back in the late 1960s, long before anyone had heard the phrase gamma-ray burst, a different kind of satellite was watching the sky. It did not belong to NASA or any civilian space agency. It belonged to the United States military, and its job was simple, at least on paper. Listen for the telltale flash of gamma radiation that would reveal a secret nuclear test on the far side of the world. These Vela satellites were guardians of a Cold War treaty, pointed outward not to explore the universe, but to keep human beings from breaking their own promises. Then they heard something that made no sense. The satellites began detecting brief, intense flashes of gamma rays that were not coming from Earth at all. They were coming from random directions in deep space. No bomb could do that. No known star could do that either. For years, the data sat classified and mysterious, until in 1973 astronomers were finally allowed to study it and gave the phenomenon its name: gamma-ray bursts. At first, nobody knew what they were. Some scientists thought they might be strange eruptions from neutron stars within our own galaxy. Others argued they had to be much farther away, the death screams of stars in distant galaxies. The only thing everyone agreed on was that whatever these events were, they released staggering amounts of energy in a very short time. But without precise positions, the bursts were phantoms. Bright, brief, and gone before any other telescope could turn to look. That changed in the 1990s and 2000s, when space agencies started launching satellites built specifically to chase these ghosts. NASA's Swift spacecraft, launched in 2004, was small and relatively modest in power. Its mission sounded almost humble: detect bursts, quickly calculate their positions, and swing its X-ray and optical telescopes toward the fading afterglow. The Fermi Gamma-Ray Space Telescope, launched in 2008, added a broader view of the high-energy sky, catching the most energetic photons and mapping their origins. Over time, a picture emerged. Most long gamma-ray bursts seemed to come from the collapse of massive stars in distant galaxies, accompanied by supernovae. Shorter bursts were linked to colliding neutron stars. They were unimaginably violent, yes, but also unimaginably far away. For decades, the working assumption was reassuring. These were fireworks on the outer walls of the observable universe, dramatic to watch but too remote to matter to life on Earth. The detectors circling our planet were treated almost like scientific weather stations, quietly logging bursts, sending out alerts, publishing catalogs. Year after year, they confirmed the same story: powerful, rare, distant. No one designing those missions expected them to record anything that would make us question our own planet's safety. Then, in October 2022, the universe sent a burst that broke their scales. Alarms lit up across control rooms, software designed to handle extreme events reporting numbers off the charts, leaving teams wondering whether their instruments were malfunctioning or the universe had shown them something new. That mysterious burst did not stay anonymous for long. In NASA logs and scientific circulars, it received a label that looks ordinary until you know what it hides: GRB 221009A. The numbers mark the date, 2022 October 9th, and the letter A means it was the first major burst detected that day. For the instruments aboard Fermi, Swift, and several other spacecraft, it did not feel routine. Their detectors, designed to handle the wildest shows the cosmos could throw at them, suddenly began screaming with a signal so intense that some of them simply maxed out. On readout screens in control rooms, plots that usually show graceful spikes and decays became flat-topped plateaus, like seismographs driven off the page by an earthquake. Software flagged overflows and saturation warnings. At first, some teams suspected an error, a glitch in the electronics, or a problem with the onboard calibration tables. Then messages started coming in from other observatories, each one saying essentially the same thing: "We're seeing it too, and our instruments are also overwhelmed." Whatever this was, it was not a local malfunction. The universe itself had just fired a shot across every sensor we had pointed upward. To understand what those machines had just witnessed, it helps to picture what a gamma-ray burst actually is. When certain very massive stars reach the end of their lives, their cores collapse under their own weight. In a fraction of a second, the star implodes, forming a black hole or an ultra-dense neutron star, and much of the outer material falls inward. Instead of exploding evenly in all directions, some of that energy is funneled into two narrow jets that blast out from the poles. Those jets move at almost the speed of light and shine primarily in gamma rays, the most energetic kind of light known. Because the energy is focused instead of spread out like a normal supernova, an observer looking almost straight down one of those jets can see an event that outshines entire galaxies for a few seconds or minutes. For decades, astronomers modeled these bursts, estimating how bright they could plausibly be and how far away we were likely to find them. They concluded that while gamma-ray bursts were impressive, there was a practical upper limit. Instruments like Fermi and Swift were built with that limit in mind, their detectors tuned to capture the strongest flashes the theories allowed without losing the shape of the signal. GRB 221009A ignored those expectations. The burst came from a galaxy roughly 2.4 billion light-years away. That distance is so large it is hard to make it feel real, so scale it this way. The light from our own sun takes about 8 minutes to reach Earth. The light from GRB 221009A had been traveling toward us since long before the first trees grew on land, and yet, after crossing that unimaginable gulf, it still hit our detectors with enough strength to saturate them. Some of the individual photons carried energies in the tera-electron-volt range, billions of times more energetic than the X-rays used in a medical scanner. Ground-based Cherenkov telescopes, which normally watch for faint blue flashes in the upper atmosphere created when high-energy particles slam into air molecules, also lit up. They recorded photons from this single burst at energies no one had confidently expected to see from such a distant source. It was as if a lighthouse on the other side of an ocean had suddenly burned bright enough to cast sharp shadows on the far shore. When teams compared notes, they realized that across the spectrum, from soft X-rays to multi-TeV gamma rays, this event was not just at the top of the scale, it was off the scale entirely. In the months that followed, papers began to appear with an acronym that captured scientists' unease and fascination. GRB 221009A was quickly nicknamed the BOAT, short for Brightest of All Time. That label is not marketing language. It reflects the fact that among tens of thousands of recorded bursts, this one sits alone at the extreme end of the distribution. For decades, models had sketched a comfortable boundary line around how much power a jet like this could carry and how focused it could be before physics itself would say no. The boat stepped cleanly over that line and kept going. This is the moment to stop and think what those numbers imply. A star you will never see, in a galaxy you will never visit, collapsed so violently that its death rivaled the light of billions of suns, and that flash pushed our detectors toward overload after crossing billions of light-years of space. When an event that distant can hit us that hard, it forces a question how close one could be and still leave anything alive. That question is not idle speculation, and it is not the language of doomsday videos. It is a calculation astronomers actually perform, with numbers, distances, and atmospheric chemistry. To see why a burst billions of light years away matters to a planet like ours, you have to imagine one much closer. Suppose a gamma ray burst fired one of its jets directly at Earth from only a few thousand light years away, well inside our own galaxy. The gamma rays themselves would not cook the surface. They would be absorbed high in the atmosphere, and that is precisely the problem. All that energy would tear apart nitrogen and oxygen molecules, driving chemical reactions that produce nitrogen oxides, the same compounds that destroy ozone. Models suggest a significant fraction of the ozone layer could vanish within days and stay depleted for years. Without that shield, ordinary sunlight becomes hostile. Ultraviolet radiation would pour down onto oceans and land, damaging plankton at the base of the food chain, scorching plants, and breaking the delicate biological machinery that most life depends on. The burst would last seconds. The consequences could last decades. Some researchers have wondered whether this has already happened. One long-debated hypothesis links the Ordovician mass extinction, roughly 440 million years ago, to a nearby gamma-ray burst. It remains speculative. There is no fossil signature that says gamma rays did this, and most scientists point to climate and ocean chemistry as more likely culprits. But the idea is taken seriously enough to keep appearing in the literature, because the physics permits it. Let me be clear about the burst we have been discussing. GRB 221009A posed no danger to Earth. It was far outside our galaxy, and its jet was not aimed precisely at us. Even the small fraction of its energy that reached our atmosphere produced only a faint, measurable disturbance in the ionosphere, detected by instruments listening to radio signals. Nothing more. And yet, that is exactly what unsettles researchers. A burst that distant should have been a whisper. Instead, it left a fingerprint on our upper atmosphere and overwhelmed spacecraft built to withstand extremes. For decades, the working assumption was that events of this intensity were essentially impossible. Now we know they are not, and every estimate that rested on that assumption has to be reopened. Astronomers build what you might call cosmic hazard maps. They combine how often massive stars die, how many of those deaths produce jets, how narrow those jets tend to be, and how densely stars are packed in different regions of the galaxy. Out of that comes a rough answer to a very human question. How frequently might a planet like ours find itself in the crosshairs? A single outlier can shift those maps. If jets can be more tightly focused or more energetic than models allowed, then the danger zone around each burst grows, and the comfortable intervals between such events may shrink. The honest position is that we do not yet know by how much. What we do know is that the numbers we trusted were incomplete. Our safety, in the end, does not rest on anything we built. It rests on geometry, on raw distance, and on the direction a dying star happens to point in its final second. That is a strange and humbling thing to sit with. And the deeper researchers dug into this particular burst, hoping to pin down how such power was possible, the less certain their explanations became. Because the Bayat did not only break old records, it broke the models meant to explain it. Breaking a record is one thing. Breaking the model that explains the record is something else entirely. In the weeks after that October morning, the excitement in observatories around the world began to curdle into something closer to confusion. The data was extraordinary. The explanations were not arriving. Those first hours were chaotic in the way only good science can be. Automated alerts went out within seconds, and astronomers on every continent abandoned whatever they had planned for the night. Telescopes swung toward a patch of sky in the constellation Sagitta. Radio dishes, optical observatories, X-ray instruments, and neutrino detectors all turned to look at the same fading point of light. Graduate students were woken by phone calls. Observing schedules built months in advance were torn apart in minutes, because everyone understood that whatever this was, it would never be repeated in their lifetimes. But there was a problem hiding inside all that data. Several of the instruments that recorded the burst were effectively blinded by it. When a detector saturates, it stops counting accurately. It knows that something enormous is arriving, but it can no longer measure how enormous. Reconstructing the true peak brightness became an exercise in careful inference, using scattered photons, secondary effects, and instruments that happened to be looking from awkward angles. Different teams, using different methods, arrived at different answers. The most extreme event ever recorded is also, in some ways, one of the hardest to measure. Then came a second surprise. Long gamma-ray bursts are supposed to be accompanied by a supernova, the visible death of the massive star that produced the jet. Astronomers watched and waited for that supernova to brighten. When they finally teased it out of the glare of the afterglow, it looked ordinary. A record-shattering burst had emerged from what appeared to be a fairly typical stellar explosion. Whatever made this event exceptional, it was apparently not the star itself. That left two broad families of explanation, and the difference between them matters more than it might sound. The first says the jet was intrinsically extraordinary. Perhaps the collapsing core produced an unusually efficient engine, funneling energy into a beam far tighter and far more powerful than anything modeled before. If that is true, then nature is capable of building weapons we did not know existed, and our catalog of what stars can do is incomplete. It would also mean the rarest events are rarer than we hoped. The second explanation is quieter, and in some ways more disturbing. It suggests the burst was not unique at all, only perfectly aimed. Jets are not uniform tubes of light. They have structure, with a narrow, blazing core surrounded by slower, dimmer material. If we happen to be staring straight down the very center of that core, we would see an event that looks impossible while the underlying star behaved normally. Under that reading, bursts like this may be relatively common in the universe. We simply almost never line up with them. There is a further wrinkle. Some of the highest energy photons detected from this burst should, in theory, have struggled to cross billions of light years without being absorbed by the faint background light that fills intergalactic space. A few researchers have asked whether our understanding of that background needs adjusting, or whether something subtler is happening in the physics of the jet. Most consider conventional explanations sufficient. Not all of them are satisfied. The honest answer, for now, is that we are arguing about a single data point. Dozens of papers later, there is still no settled verdict. That is not a failure of science. It is what the edge of a map looks like. But it leaves us holding an uncomfortable piece of knowledge. We now know that bursts of this magnitude are physically possible. We do not know how often they occur, how tightly they are focused, or how close one could be before our instruments had any warning at all. Answering that requires more examples, and the only way to collect them is to keep watching and wait for the universe to fire again, which is exactly what the next generation of observatories is being built to do. That waiting has a schedule. For most of the history of this field, astronomers could only sit still and hope, watching a sky that offered its rarest events on its own terms. The next few years are different, because for the first time we are deliberately building a net wide enough to catch whatever comes next. The gravitational wave observatories are central to that effort. LIGO in the United States, Virgo in Italy, and CAGRA in Japan have spent years upgrading their mirrors and lasers, pushing toward sensitivities that were considered unreachable a decade ago. Their next extended observing runs, scheduled through the second half of this decade, are expected to detect neutron star collisions at rates that would once have sounded absurd. Above them, a new generation of small, fast satellites is taking shape. NASA's Burst Cube, a spacecraft roughly the size of a shoebox, was designed to watch for gamma-ray bursts from low Earth orbit and prove that useful science does not require a bus-sized observatory. Mission concepts in the class of the European Space Agency's TESIS proposal aim further still, promising to locate bursts across most of the sky and identify their host galaxies within minutes. Put those capabilities together, and something genuinely new becomes possible. Instead of studying a burst through a single narrow window, astronomers could watch the same event in gravitational waves, gamma rays, visible light, and radio at once. Each messenger carries different information. Combined, they can reveal the shape of a jet, the angle we are viewing it from, and the machinery hidden at its base. That is precisely the test our theories need. If the coming observing seasons deliver another burst approaching the intensity of the one recorded in 2022, then the quiet explanation wins, and events like it are simply waiting for us to look in the right direction. If years pass and nothing comes close, the case strengthens that we witnessed something close to a once-in-a-millennium alignment. The next few years will not be neutral. They will act as a verdict. Here is the part that gives this a strange urgency. The next burst is not a hypothetical. Somewhere in the sky tonight, a massive star has already collapsed. Its light has already been traveling for millions or billions of years, crossing distances no human vehicle will ever cover, moving toward a small blue planet whose inhabitants are only now learning how to listen. The event is finished. The message is still in transit. We cannot slow it, redirect it, or delay its arrival. Whether our instruments are ready when it arrives is the only variable we control. When that signal finally reaches us, it will settle arguments that dozens of papers could not, and I will be here to walk you through exactly what it means. But whichever answer the universe gives, it will arrive over the same fragile world, witnessed by the same brief civilization that built the machines waiting to receive it. Step back far enough from all of this, and something quietly astonishing comes into focus. The layer of air protecting every living thing you have ever known is thinner, proportionally, than the skin on an apple. If you could drive straight upward at highway speed, you would pass through most of it in under an hour. That fragile shell, and the magnetic field wrapped around it, is the only thing standing between us and a universe that was never designed with us in mind. Because the universe is not hostile. Hostility would at least imply attention. It is something colder than that, indifferent. Stars collapse, jets fire, galaxies collide, and none of it takes any notice of the small warm worlds that may be caught in the crossfire. Events like the one we have been discussing are not rare accidents in the cosmic story. They are part of how the universe routinely operates, and they have been happening for billions of years, most of them long before anyone existed to record them. And yet, hold that fragility in one hand, and hold this in the other. On an ordinary Sunday in October, a flash of radiation that had crossed roughly 2.4 billion light years arrived at Earth, and we noticed. Not decades later. Not by accident. Within seconds. Machines no larger than a car, built by teams working with budgets smaller than a single commercial aircraft, registered the event, calculated its position, and sent alerts racing around the planet before most people had finished breakfast. Think about what that requires. A species that has existed for a few 100,000 years, on a planet orbiting an unremarkable star, has learned to read light it cannot see, from a star it will never visit, and to work out how that star died. We built the mathematics. We built the detectors. We trained the people who knew what the numbers meant when the alarms went off. That is the strange dignity of our position. We are, as far as we know, the only thing in this galaxy capable of measuring the forces that could end us. Vulnerability and understanding arrived together. The same curiosity that built the Vela satellites, and later Apollo, and later Voyager, is the curiosity that now lets us put numbers on our own exposure. We cannot stop a gamma ray burst. We can, however, know that it exists, and that knowing is not nothing. There is something almost sacred in that exchange. The same physics that forges carbon in dying stars and scatters it across space, the physics that made your bones and the iron in your blood, is the physics that lights those jets. The universe that can erase us is the universe that assembled us. Nothing else has ever stood beneath that sky and understood both halves of the sentence at once. To measure the thing that could destroy you and still look up in wonder may be the most human act there is. This story is not finished, and neither is the science. If you want to be here when the next record-breaking burst arrives, and when researchers finally decide whether that October flash was a warning or an outlier, subscribe and turn on notifications. I will bring you the answer the moment it lands. Before you go, tell me in the comments which part of this surprised you most, and whether learning about these bursts leaves you frightened or strangely inspired. I read every reply. And share this with someone who still believes space is empty and safe. It is neither.